Next, let us see how to calculate the integral of rational functions. So recall that the rational function was a function of the form px divided by qx, where both px and qx are polynomials. And now we want to calculate the integral of this rational function px over qx. The way to tackle this problem will depend on the degree of both polynomials. So if the degree of p of x is at least as large as the degree of q of x, then we first perform Euclidean division. So you first perform your division such that you can rewrite p of x divided by q of x as d of x plus a remainder r of x divided by q of x. And because of your division, the degree of r of x will always be strictly smaller than the degree of q of x. Take, for example, the integral of x to the power 3 plus 3x squared divided by x squared plus 1 dx. Clearly, this is a rational function. We have a polynomial of degree 3 in the numerator, and we have a polynomial of degree 2 in the denominator. We see that the degree of p is larger than the degree of q, so we have to first do the division. So for the division, you have x to the power 3, 3x squared, 0x, 0, and then you divide out by x squared plus 0x plus 1. Here we have x times, this gives me x to the power 3, 0, x squared, and x. We subtract, so this gives me 3x squared minus x. Here in 3x squared, x squared goes 3 times, so this gives me plus 3. 3 times q of x gives me then 3x squared plus 0x plus 3. Then we do the subtraction and we get minus x minus 3. So the result of my division is now x plus 3, this is my d of x, plus my remainder, minus x minus 3, divided by q of x, which is x squared plus 1. And now we have to take the integral of this entire thing. The integral of x is just x squared divided by 2. The integral of 3 is 3x. And then we have minus the integral of x dx over x squared plus 1 minus 3 times the integral of dx divided by x squared plus 1. For this first integral, you can do a substitution. So set x squared plus 1 equal to u, and then 2x dx is equal to du. The second integral we can immediately calculate. So this becomes x squared divided by 2 plus 3 times x minus then the logarithm of x squared plus 1 minus 3 times the inverse tangent of x plus a constant. So now we still have to look at what happens if the degree of p of x is strictly smaller than the degree of q of x. In this case, the complexity of the problem will depend on the degree of q of x. First, assume that we have a linear denominator. So basically the degree of q of x is equal to 1. Since the degree of q of x is 1, we can write q of x as a times x plus b for some values a and b, and a is different from 0, because we have a linear denominator. So if this is the case, then we also know that the degree of p of x is 0 because the degree of p is strictly smaller than the degree of q. So this means that p of x is equal to a constant d. As such, my integral is of the form d divided by ax plus b dx, and the solution of this kind of integral is easy to find using substitution. So this is d divided by a times the logarithm of ax plus b plus a constant. For the second case, assume that we have a quadratic denominator. So the degree of q is equal to 2. In this case, we can always assume that q of x is either of the form x squared minus a squared or of the form x squared plus a squared. So this can be obtained by completing the square. And we will come back later to this thing. So we will see later how to complete the square. But for now, we will just assume that q of x is of the form x squared minus a squared or x squared plus a squared. Since the degree of q of x is 2, and we know that the degree of p of x is smaller, so this means the degree of p of x is either 0 or it is 1. As such, we can distinguish 4 different cases. So you will have the integral of x dx over x squared plus a squared. You have the integral of x dx over x squared minus a squared. You have the integral of dx over x squared plus a squared. And then finally, the integral of dx divided by x squared minus a squared. For the first case, you can perform a substitution, set u equal to x squared plus a squared. If you do this, you will find that the solution for this integral is 1/2 times the logarithm of x squared plus a squared plus a constant. The second case is very similar. You set u is x squared minus a squared as substitution, and then the solution becomes 1/2 times the logarithm of x squared minus a squared plus a constant. For the third integral, we can rewrite this. So we know the integral of dx over x squared plus 1. So what we will be doing is take out the a squared. So here you get a squared times x over a squared plus 1. And then you just perform an easy substitution. So you set u equal to x over a. If you then solve this integral, you will find that this is equal to 1 over a times the inverse tangent of x divided by a plus a constant. And then the fourth case, which is a little less obvious, we will see how to do it, but the solution for this is 1 divided by 2a times the logarithm of x minus a divided by x plus a plus a constant. So how do we find this last formula then? What we will do is we'll try to write the integrand as a sum of two fractions with linear denominators. So we see we have 1 over x squared minus a squared. X squared minus a squared is x minus a times x plus a. And then we will try to split this. So we now have a multiplication in the denominator, and we will try to make this expression into a sum of two fractions. So we have, or we will get, something on x minus a and something on x plus a. Question then is, what are the numerators? So for now we can call them a and b. The numerators will be constants. Because on the left we also have a numerator of 1, so we have just a number. We have no x, no variable in the numerator. So on the right hand side we now have a over x minus a plus b over x plus a. And then we will rewrite this, so we will bring this on the same denominator. And so the numerator is a times x plus a plus b times x minus a. We now have two expressions for the same thing. So on the left we have 1 over x squared minus a squared. And on the right we have a times x plus a plus b times x minus a, also over a squared minus a squared. And logically these two have to be the same. Therefore we get 1 is equal to a times x plus a plus b times x minus a. So this is a times a minus a times b plus x times a plus b. And then we have to have that the left hand side and the right hand side are the same. So this means that a times a minus a times b is the same as 1. So this is my constant term. And then the second one is a term in x, so a plus b. This is a term of the first order in x, which is not present on the left. So here this has to be equal to 0. You can then solve this set of equations. And you will find in that case that capital A is 1 divided by 2a. And capital B is minus 1 divided by 2a. So my integral then becomes the following. So I had the integral of 1 over x squared minus a squared dx. I just rewrote 1 over x squared minus a squared as 1 over 2a x minus a minus 1 over 2a x plus a dx. And then we can split this. So this is 1 over 2a, the integral of dx over x minus a, minus the integral 1 over 2a dx over x plus a. Both integrals are easily solved. They will be logarithms, so we obtain 1 divided by 2a ln of x minus a minus ln of x plus a, and then with the brackets, plus a constant. And then we use a basic logarithmic formula. So we know that a difference of logarithms is a logarithm of the fraction. So this is 1 over 2a ln of x minus a divided by x plus a plus a constant. This method of writing a fraction as the sum of simpler fractions is called the method of partial fractions. How does it work in general? So we have qx, so we have that qx is a polynomial of degree n. And we can factorize this polynomial. So we can factorize this qx as x minus a1 times x minus a2 up to x minus an. So we have n roots because the degree is n, and for now we will assume that all the roots are distinct. So ai is different from aj for all I and j. So we have in this case all distinct roots. If we then take another polynomial p of x, and this p of x has a degree which is strictly smaller than the degree of q of x, so strictly smaller than n, then the division p of x divided by q of x has a partial fraction decomposition. So partial fraction decomposition, which is equal to p of x over q of x is a1 over x minus a1 plus a2 over x minus a2, and so on up to an over x minus an. The only thing that then remains is to find the values of those numerators. So find the values a1, a2 up to an. How do we find the values? Well, you take the right hand side and you place everything on the same denominator. So for the right hand side, place everything on the same denominator, which then gives you something s of x divided by q of x. And then you know that the left hand side and the right hand side have to be the same. So then you have p of x is s of x. This s of x, this one depends on a1 to an. And so you get a set of equations which allows you to solve for a1 to an. Let's illustrate this through an example. So we have the integral x to the power 3 plus 2 divided by x to the power 3 minus x dx. We see that the degree of the numerator is 3, but also the degree of the denominator is 3. So to apply our method, the degree of the numerator has to be smaller than the degree of the denominator. And so we first have to reduce this degree. Either you perform the Euclidean division to find this degree, or you can apply a trick in this case. So we just take this integral, so x to the power 3 plus 2. And now we see on the bottom we have x to the power 3 minus x. And what we want to do is we want to reduce this. So we want to reduce the maximal power. What we can do is do minus x plus x. So actually we just add 0. But this will allow us to split the integral in two parts. So if we then split it, you get x to the power 3 minus x over x to the power 3 minus x dx, plus the integral of x plus 2 over x to the power 3 minus x dx. The left one is just 1, so this is x. And then the other integral, this is x plus 2 over x to the power 3 minus x dx. So here, the degree of the numerator is 1, which is strictly smaller than the degree of the denominator, which is 3. We will then try to split this into partial fractions. So if we look at it, so we have x plus 2 divided by x to the power 3 minus x. X to the power 3 minus x, you can take out one of the x's. And then you have x squared minus 1. X squared minus 1 is x minus 1 times x plus 1. And so we have 3 components in my multiplication. So if I want to split this, I will also get a sum of 3 parts. So I get something on x plus something on x minus 1 plus something on x plus 1. Let's call these somethings, these constants a, b, and c. Why a, b, and c? So why do we take constants? Because in the method of partial fractions, the degree of the numerator always has to be 1 lower than the degree of the denominator. In this case, the denominator has degree 1, so it is linear in x, which means that the numerator has to have a degree 0, it has to be a constant. In the next step here, we bring everything on the same denominator, so x times x minus 1 times x plus 1. This is a times x squared minus 1 plus b times x plus 1 plus c times x minus 1. And then the left expression has to be equal to the right expression. So you have these two expressions which have to be the same, which allows you to find a, b, and c. Let's write this down. This gives me that x plus 2 is equal to a times x squared minus 1 plus b x plus 1 plus c x minus 1. Let's then group the powers of x. So in x squared we have a plus b plus c. Then in x, what do we have in x? In x we have b minus c. And then finally the constant term here is minus a. The degrees of x have to have the same coefficient. So this means that a plus b plus c which is the coefficient of x squared on the right hand side, has to be 0 because there is no x squared on the left hand side. Same thing, b minus c is the coefficient on x on the right hand side, has to be equal to 1, which is the coefficient of x on the left hand side. And then minus a, which is the constant term, has to be equal to the constant term here, 2. So I have a set of equations. I have 3 equations for 3 unknowns, and I can then find a solution for a, b, and c. To solve this, you immediately see that a is minus 2. And then from the second equation, you find that b is 1 plus c. You plug these two in the third equation, so a plus b plus c is 0. So a was minus 2, b was 1 plus c, and then c, this has to be 0. And therefore we find that c is 1 over 2 and b will be 3 over 2. So let's go back to the integral. So the integral was x plus the integral of x plus 2 over x to the power 3 minus x dx. The partial fraction decomposition that we found for this was minus 2 over x plus 3 over 2 times 1 over x minus 1 plus 1 over 2, 1 divided by x plus 1. So the integral becomes x plus the integral of the first part plus the integral of the second part plus the integral of the third part. So it is x minus 2 times the integral of dx over x plus 3 over 2 the integral dx over x minus 1 plus 1 over 2 the integral of dx over x plus 1. Then we work it out, so it's x minus 2 times the logarithm of x plus 3 over 2 times the logarithm of x minus 1 plus 1 over 2 times the logarithm of x plus 1 plus a constant. When we look back at the decomposition of q of x, we actually made 2 assumptions. First, we assumed that all of the roots are linear, so all of the terms in the decomposition are linear. And secondly, we assumed that all the roots are different. Both of them don't have to be true, and so we have to make a more general statement of a partial fraction decomposition. Let's first start with the case of linearity. So assume that here in the decomposition of Q, that this also contains non-reducible, so non-reducible quadratic terms. So it contains second order terms, x squared plus something, which can no longer be reduced to linear terms. So they cannot be reduced, they cannot be further factorized than a quadratic term. If you have this, in that case, the numerator will not be a constant, but will be linear. As we already said before, in partial fraction decomposition, the numerator is always 1 degree smaller than the denominator. And so if the denominator is quadratic, so the degree is 2, the numerator has to be linear, has to have a degree of 1. Same thing, let's just illustrate this immediately with an example. So take the integral dx over x to the power 3 plus 1. We know that x to the power 3 plus 1 is equal to x plus 1 times x squared minus x plus 1. And then the second factor, x squared minus x plus 1, this cannot be factorized into linear terms, so we cannot find a further factorization. The discriminant of this is smaller than 0. If we then look at the partial fraction decomposition, we have 1 over x to the power 3 plus 1. So here we get something on x plus 1 plus a second term on x squared minus x plus 1. Because we cannot further factorize this, we have to keep it as this. We then said that the degree of the numerator has to be 1 smaller than the degree of the denominator. So here the first term is x plus 1. Degree is 1, so the degree of the numerator has to be 0. This is just a constant. And then for the second part, we have x squared, so we have a quadratic term. Degree is 2, which means that the degree of the numerator has to be 1. So we have to have something with an x and a constant, so bx plus a constant, a linear term. And then the solution is the same, so we work on the same way. We bring everything back on the same denominator. And now we say that the left-hand side and the right-hand side have to be the same. So this one has to be the same as this expression. We compare the different degrees, so we have a degree for x squared. On the left-hand side, this is 0. On the right-hand side, we have a plus b. The degree for x on the left-hand side is 0. On the right-hand side, we have minus a plus b plus c, and then the constant. The constant on the left-hand side is 1, and on the right-hand side, this is a plus c. So here as well, we have 3 equations and 3 unknowns, so we will find a unique solution for this set of equations. So the first one, this tells me that a is minus b. If we then combine this with the second equation, we find that 0 is minus a plus c. So c is equal to 2a. And now we combine c equal to 2a with a plus c is 1. So we find that 1 is a plus 2a, or a is 1 divided by 3. If a is 1 divided by 3, b is minus 1 over 3, and c is 2 over 3. We then plug this decomposition in the integral, so my integral becomes 1 over 3 times the integral of dx over x plus 1 minus 1 over 3, the integral of x minus 2 divided by x squared minus x plus 1 dx. And to solve this, what we will do is we will complete the square. So what we said before, we will come back to completing the square. So completing the square. What we do here is you have a quadratic expression. A general quadratic expression of ax squared plus bx plus c, which you will often find in integrals. What you will do by completing the square is to transform this into something of the form x squared plus a squared or x squared minus a squared. And the way to do this is based on the formula a plus b squared is a squared plus 2ab plus b squared. So this is the important formula in completing the square. In this case, what we have is x squared minus x plus 1. So we see, if we compare, we have here x squared, which corresponds to my a squared, minus x will correspond to plus 2ab, and then the question is, what is my b squared? Since a squared is x squared and 2ab is minus x, we see that b will be minus 1/2, and so b squared will be 1/4. So x squared minus x plus 1, this is equal to x squared minus x, and now we need 1/4 to complete the square, so to make it a full square. And then we have 3 over 4 left. Because we have a factor, we have a constant term of 1, we split this as 1 over 4 plus 3 over 4. And then this expression is just x minus 1/2 squared plus 3 over 4. So by completing the square, we will always find something of the form u squared plus some a squared, or u squared minus a squared. And we saw before how to solve integrals of this form. We saw this a couple of slides before in this same chapter. Let's now focus for a moment on the subintegral, so only the integral x minus 2 over x squared minus x plus 1 dx. So we saw that this is x minus 1 over x minus 1/2 squared plus 3 over 4 dx. Then perform a substitution, u equal to x minus 1/2. So this means that du is equal to dx. So we get the integral of u minus 3 over 2 divided by u squared plus 3 over 4 du. We can then split it, so this is u du over u squared plus 3 over 4 minus 3 over 2 times the integral du over u squared plus 3 over 4. We have seen how to solve these kind of integrals. So this is 1/2 times a logarithm of u squared plus 3 over 4 minus 3 over 2 times 2 over root of 3 tangent minus 1 u divided by root 3 over 2 plus a constant. We then have to transform everything back to x. So it's 1 over 2 times the logarithm of x squared minus x plus 1 minus root of 3 times the inverse tangent of 2x minus 1 divided by root 3 plus a constant. And then as a last step you have to plug it into the original integral. So you have to plug it into the black integral on the previous slide. And so the final integral, this becomes 1 divided by 3 ln of x plus 1 minus 1 over 6 times the ln x squared minus x plus 1 plus 1 over root of 3 times the inverse tangent of 2x minus 1 divided by root 3 plus a constant. So we already solved the case for non-linear factors in your decomposition. Now what happens if some of the roots are not distinct but they are repeated? So if in the decomposition of Q some factors are repeated, let's say m times, then the partial fraction decomposition so this decomposition will require m terms with increasing exponent. So we have exponents going from 1 to m. And this while the denominators, these remain linear or constant. So in this case we have no powers in the denominators. So for example, if I have a fraction which looks like this, ax plus b squared times cx squared minus d to the power 2. If I want to make a decomposition of this, I see there are two different factors, ax plus b, and this appears 2 times, and cx squared minus d, which also appears 2 times. So I will have, according to the rule, ax plus b once, and then I repeat it, ax plus b, but with a power 2, and then also cx squared minus d and cx squared minus d squared. So I require the same amount of terms in my decomposition as the power of the factor. So here I have a power 2. I have this factor twice, which means that I have it once here and the second time there. And then we said that the powers, the exponents have to increase. So for the first one, here the power will be 1, and then the second one will have a power 2. Similarly, for the second factor, cx squared minus d, this also has a power 2. So I get a first term and a second term. and for these also with power 1 and power 2. Then what are the numerators that we need to use? So we said that the numerator, the degree of the numerator, is always 1 less than the degree of the denominator. For the first term, we have ax plus b, so the degree is 1, which means that the degree of the numerator has to be 0, so we get a constant term here. So it's a divided by ax plus b. Furthermore, the second one, ax plus b squared, basically the factor is the same. So the factor is still ax plus b, which is still a linear factor. And so the numerator still has to be a constant term. So here we have a b, and we do not increase this to the power 2. So we just keep, it's a constant b, because the factor is ax plus b. And then similar for the final two terms. So there we have cx squared minus d. So we have a quadratic term, which means that the denominator has to be linear, so of degree 1. So we get cx plus d, and here the second one, ex plus f. So here again, we have a linear numerator for a quadratic denominator, and we do not take the power which comes from the repetition into account. So this one, the numerator, does not get increased by the power. To make this clear, let's illustrate this on some examples. So, for example, take the integral of 1 over x times x minus 1 squared dx. So we have 1 over x minus x1 squared. And we want to make a partial fraction decomposition of this. So we see that there are 3 terms. You have x and then x minus 1 to the power 2. So we have a term 1 over x. We will have a term over x minus 1. And then, because there is a repetition, we also get x minus 1 squared. Then what are the numerators? So the first one is linear denominator, which means I have a constant in the numerator, so it's x. The second one is also linear, so degree 1, the power of the numerator will be degree 0. And here, x minus 1 squared. The factor is still x minus 1, so it's still a linear factor, which means that I have a third constant as a numerator. We then put everything on the same denominator, which gives me a times x minus 1 squared, plus b times x minus 1, plus c times x. And then again, the left one and the right one, they have to be the same. This means that 1 is equal to a times x squared minus 2x plus 1 plus b times x minus 1 plus c times x. We can then equate the different terms. So in x squared on the left hand side it's 0. On the right hand side I have a plus b. The linear term, so the one in x on the left hand side is 0. On the right hand side it's minus 2a minus b plus c. And then for the constant term we see that 1 is equal to a. So if 1 is equal to a, the first one tells me that b is equal to minus 1. And then if we use that, then we can find that c is also equal to 1. Therefore, the integral becomes the integral of dx over x minus the integral of dx over x minus 1 plus the integral of dx over x minus 1 squared, which is equal to the logarithm of x minus the logarithm of x minus 1 minus x minus 1 to the power minus 1 plus a constant. To conclude, let's calculate the integral. So the integral of 1 minus x plus 2x squared minus x to the power 3 divided by x times x squared plus 1 to the power 2 dx. Let's first calculate the partial fraction decomposition. So 1 minus x plus 2x squared minus x to the power 3 over x squared plus 1 squared. Here this will be something over x, so a constant over x, plus, and then we have x squared plus 1. This is the second factor. We cannot factorize this anymore. We cannot split this in lower order terms, so it's x squared plus 1. Second order, which means that the numerator has to be of the first order, so it's bx plus c. And then this factor appears twice, so we also get x squared plus 1 to the power 2 in my partial fraction decomposition. And here the numerator again is a linear term, so dx plus e. Then bring everything on the same denominator, so x times x squared plus 1 to the power 2. Then we get a times x squared plus 1 to the power 2 plus bx plus c times x squared plus 1 plus dx plus e times x. If we then look at the set of equations that this will give us, we have up to power 4, so we have something x to the power 4, x to the power 3, x squared, x and a constant term. In x to the power 4, we see that we have a plus b on the right hand side and 0 on the left hand side. For the third power, we see that we have c on the right, minus 1 on the left. In x squared, we have 2a plus b plus d on the right. This is equal to 2 on the left. Then c plus e equal to minus 1 and a equal to 1. And so we have now 5 equations for 5 unknowns. We see immediately that a is equal to 1, c is equal to minus 1, and then you can use this to solve the rest. Since a is 1, this means that b is minus 1 because of the first equation. Then, since c is minus 1, the fourth equation tells me that e is equal to 0. And then all the rest, so we combine this in the third equation, tells me that d is equal to 1. So we have found a solution. A is 1, b is minus 1, c is minus 1, d is 1, and e is 0. We plug then those values into the partial fraction decomposition, and the integral becomes the integral of dx over x minus the integral of x dx over x squared plus 1, then minus the integral of dx over x squared plus 1, and then finally plus the integral of x dx over x squared plus 1 to the power 2. For the second and the fourth one, you can do a substitution. So u is equal to x squared plus 1, which means that du is 2x dx, and this allows you to easily calculate the integrals. We then obtain that this is equal to ln x minus 1/2 times the integral of du over u minus the inverse tangent of x plus 1/2 times the integral of du over u squared. We then calculate the integrals and we make a substitution back. So in the end we get ln of x minus 1/2 times ln of x squared plus 1 minus tan minus 1 of x minus 1/2 of x squared plus 1 to the power minus 1 plus a constant.